Good evening and welcome to my report on the Cleveland Wastewater Treatment Plant. This report will analyse each of the treatment processes the plant utilises in the cleaning of wastewater collected from the Redlands area before it is released back into environmental aquatic systems. The site is located on Weepin Street, Cleveland, in a section of a national park known as Weepin Street Conservation Area. As seen on this map of the area, the treatment facility is located on the red dot. The blue dot represents the primary discharge station of the facility from an outflow pipe into Hillards Creek attached to the Logan Albert Basin. The second discharge point is located on the yellow dot on the map, where the water is released at an outlet of storage lagoons prior to the treated wastewater irrigation area. So what exactly is wastewater, and where does it come from? The wastewater the Cleveland treatment plant facilitates is water which has been polluted through general human usage, either commercially or in general household living in the Redlands City Council area. As a result of this, the treatment plant staff discussed how the facility takes in abnormal influxes of water in both the morning and the afternoon, roughly between the times of 6 and 10 o'clock. This is because at these times, people are most likely to use their showers, toilets, washing machines, and so on. The wastewater is treated through 5 primary process systems as seen on the map provided, which will remove solids, organic matter and nutrients from the water so it can be safely released back into natural waterways. Screening is the first stage of the treatment process, whereby the system will screen out large objects which have been flushed down the sewage system such as plastics and sanitary items. The water is then moved to the bioreactor, which will remove large amounts of nitrogen, phosphorus and carbon from the water. From there, the water is then moved to large clarifier tanks, where suspended solids are separated with the water, giving it a clear appearance. These suspended solids are then transferred to the belt filter press, where any remaining water is subtracted and put back through the bioreactor. And finally, in the 5th stage of the plant, the water is disinfected with the use of chlorine gas exposure. The first stage in the treatment process is known as screening. It is vital for the facility to have top-of-the-range technology in the screening process systems, as according to plant staff, the facility will screen out hundreds of kilos of waste from the water per day. The majority of these objects include nappies, women's sanitary items, cotton buds, plastics and towels, which will inevitably block up and damage other equipment in the plant's treatment process. The facility shown here uses a range of processes to clear various sized objects from the water, the most significant of which is what the plant staff describe as a vortex-like chamber, which will spin the water in a whirlpool-like manner, forcing all solid objects, including grit, to the edges of the container where they will be collected and sent to landfill. The next stage in the treatment process uses a series of large concrete processing tanks, known as a bioreactor. Initially, the water will flow into the anaerobic tank, as seen in the video. Here, a metal-based coagulant is added to the water in order to convert phosphates from the water into an insoluble form of aluminium phosphate, which then precipitates down into the biological growth at the bottom of the tank, which is then frequently cleared and sent to landfill. The water then flows into the anoxic chamber of the bioreactor, as shown here. The water will pass through this section twice, although the first time it passes through, heterotrophic bacteria in the water will aid in the consuming and lowering of carbon levels in the water. Next, the water passes into an aerobic zone, which as you can see, the water has now become turbulent. In doing this, the facility is pumping oxygen into the water, which reacts with any remaining carbon as well as autotrophic bacteria added by the facility, which will inevitably result in the conversion of ammonia in the water into nitrate. In the final stage of the bioreactor, the water is transferred back into an anoxic chamber, where newly created nitrates in the water react with the heterotrophic bacteria and are converted and released as nitrogen gas. The water is then moved through a series of pumping stations, as shown here, into one of the 2 large clarifying tanks. The purpose of these tanks is to separate any remaining solids in the water and to give it a polished finish. The water from the bioreactor will flow into the centre of one of these tanks, where sediment will be collected on the bottom and the clean water will be skimmed off the top. The idea behind this process is that the water is pumped into one of these tanks at a specifically calculated rate, which will cause the water levels to rise at a speed slower than the terminal velocity of the particles sinking through the water. Because of this, the water coming from the clarifying tanks should have a very little to no suspended particles within it. The remaining sediment at the bottom of the tank is consistently being cleared and is moved into the next stage of the process, known as the belt filter press. In an effort to reduce total waste going to landfill, this stage is designed to collect the sediment at the bottom of the clarifier tanks and put it through a range of filtering processes in an effort to extract as much water as possible from the sediment and provide a more solid waste product to be sent off for final landfill. As seen in the video, the machine uses a series of belts and presses in order to squeeze as much water out of the sediment as possible through the belt and into a collection tank at the bottom. The final stage of the processing plant is known as chlorine disinfection. This process involves the clarified water being exposed to chlorine gas in a series of chambers in an effort to destroy target bacteria, viruses, and organisms by oxidizing their cellular material. Chlorine is the most widely used disinfectant for municipal wastewater, as it is reliable and effective with a wide range of pathogenic organisms and is more cost effective than UV and ozone disinfection. After disinfection, chlorine residuals can persist in the water for many hours, and in order to reach an adequate level of dechlorination, therefore must sit through these concrete channels before being discharged into local waterways. Through each of these processes, the final product will be consistently tested and monitored to ensure the Redlands waterways are kept healthy and safe for all natural ecosystems in the area. Thank you for listening.